Okay, YouTube, in this video what we're going to do is confront converting equations from rectangular to polar form, essentially, but also from polar to rectangular form. And again, what we're doing is just emphasizing the relationship between the two different forms here. X and Y tell us how far left and right, up and down to go, but also if we express this in polar form, then we have some angle that we're heading in, or direction that we're heading in, and some distance that we're heading out from the origin to get to the very same point. And so our relationships between x, y, and r and theta are just clutch here. We've got these right over here on the left-hand side. And so we would say that we can actually graph of course, things in rectangular form, but sometimes it's going to be more convenient if we express their equations in what we call polar form. And so what we're going to do is we're going to look at basically a couple of basic graphs here that you see in the rectangular coordinate form that are often converted maybe into polar form, and look at how this equation in polar form really does represent the set of solutions that its rectangular form equation does. And so one thing I kind of want to start with is this: the equation of a circle that is centered at the origin. And this is just a type of equation that we often deal with polar form equations. So we're going to say that graphs of circles centered at the origin, or centered at 0, 0, in the rectangular coordinate plane are given as x squared plus y squared equals r squared, where r is the radius of our circle here. And so just to look at this couple of examples right here, I'm going to ask, would you please and thank you, would you go graph x squared plus y squared equals 9? And so, the first thing we want to recognize here is this: if x squared plus y squared equals r squared, then r squared is equal to 9. And by taking the square root of both sides of this, we could see that we get a 3 for the value of r here. And so essentially what we're doing is we're saying that this is a circle with a radius of 3. I've always told people, of course, if you have graph paper even, you can sketch this by hand, but go out 3 north, south, east, west, and just kind of put dots there, because these will have to be points on our circle. And then to the best of your ability, I always, when I'm doing this with the paper, I always turn my paper. When I don't turn my paper, I always end up with like a thing that looks like kind of a football or something like that, or maybe an amoeba. We say here's our circle of radius 3 here. And so looking at letter B, how would B be any different than this right here? You could see that the only difference really is that our radius squared value is 25, and therefore that our radius value would be 5. So again, let's go ahead and sketch this out here. And the neat thing for me is this: I say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll go 5 to the west here, and we'll go 5 south. Essentially, here's what I want to know. How is this any different from the picture I just drew over there on the left? Now, I know we don't have to have a circle centered at the origin. We could have circles centered many other places, as a matter of fact, but I just want to pay attention right now to some easier type equations. So we're going to use a circle centered at the origin, but what's the difference between these two really? Just kind of how we label it here. So the radiuses, radii, are different, but essentially they're kind of the same form here. So now, when we convert from rectangular into polar, here's going to be the thing here. We are trying to go from x and y. So go from x and y to r and theta. And so what we're going to be seeing is a situation where we want to, as much as possible, take expressions in x and y like this and write it as an r, okay? Or take an expression, an x and y like this and write it as a theta, okay? Or we could say, here's our r cosine theta. If we had an r cosine theta, that'd be the same thing as x. So maybe everywhere we see an x, we could rewrite it in r cosine theta form. That would be an r and a theta. Or maybe wherever we see a y, we could rewrite that as r sine theta. So what I'm going to tell you is that it's not just an exact science all the time, but what I'm going to say is I can give you some suggestions on how we rewrite these into polar form. So my first suggestion is going to be this: replace all x with r cosine theta. If you do this, then you've successfully changed all x's into r's and thetas. And we're also going to replace, you guessed it, replace all y values with what? All y with, well, y equals r sine theta. So we have r sine theta. So this is going to be most helpful here. Also, we're going to look for this: replace any x squared plus y squared. Now, what does that equal? Well, we know that equals an r squared, like that right there. Okay, and we could replace any y over x with the tangent of theta, and that would be in terms of a theta here. So you can see how we're changing all of our chips in here for all r and theta e kind of things. So when I look down here, really my number one suggestion is going to be take your rectangular form equation here. We have x squared plus y squared equals r squared, okay? So in this case, x squared plus y squared equals 9. But essentially, what I want to point out to everybody here is this. We would say that because x squared plus y squared is r squared, and we're trying to go into r's and thetas, what we could do is we could just simply call this an r squared here just by a substitution. And so we'd say using this x squared plus y squared equals r squared substitution, we now know that r squared is equal to 9, and taking the square root of both sides of this here, we're going to put a box around this, and we're going to say that this is our polar form equation. And this polar form equation is the same graph as x squared plus y squared equals 9. And so one thing I want to point out is you can see how much more elegant it is to write a circle instead of x squared plus y squared equals 9. It's just literally r equals 3. And as we go over to our, say, polar coordinate plane here, the neat thing is with decimals we can switch back and forth. Let's say I did want to graph x squared plus y squared equals 3. We say x squared plus y squared equals 9. And that wasn't 3, it was 9. We can see our circle of radius 3 here. But what I'm going to do now is I'm going to click back over to polar. Not that I need to click back over to graph this, but I'm going to say r equals 3. And the coolest thing happens. You can see that you get this circle with a radius of 3. But really what we're saying is, looking at all the points on the exterior of this, and I really wish I could highlight them for you, but we say, what do all of the points on the outside of this have in common? Do they share a common r value or a common theta value? And we can see that they have all these different theta values, but they're all 3 away from the origin. So we're saying that this is the equation that has all the points on it that satisfy that r equals 3. And that's pretty profound. Okay, so let's go back now and look at our second circle here. What would this look like here? Now you notice that by identifying the radius in the first place, 5, we've kind of already got the equation. But again, if you're starting off with something like x squared plus y squared equals 25 here, then again, what I want you to spy here is everywhere you see an x squared plus y squared, this is an r squared, and we get 25 there. And so r is 5, and we say that this is our polar form equation. Okay, so that is with circles, and you're going to notice something unique with circles. We always get, if it's centered at the origin, r equals whatever the radius of the circle is there in polar form. So now let's take a look at these 3 graphs over here. Now the interesting thing about it is that I want to sketch these in rectangular form first, but then rewrite the equations in polar form. And so what I want you to see about all of these equations is that they are lines. So let's say a line, the equation of a line in slope-intercept form. Slope-intercept. Just really quickly, let's recall that we have an equation that's in y equals mx plus b form, where m is our slope. We also look at slope as our rise over run, okay, rise over run. But also our b value, which is really our y-intercept. We say 0 comma b is on the graph, and that is our y-intercept on our graph. So if we're going to sketch this first graph here, y equals x, what we would get is something that has an m value of 1. We say y equals 1x plus 0 is the same thing as y equals x. We had an m value of 1 and a b value of 0. So to sketch this, we'd start by putting a point at 0 on our y-axis, and we go up 1, right 1. And we'd say, okay, so here is the graph of this rectangular form equation here. I'm going to label this. We say y equals x. How would I write this in polar form? And so unlike the last problems here where we had circles where it said x squared plus y squared, where we could just substitute in an r squared, let's roll back up to our list here and say, well then what is it that I do have that I can make substitutions for in terms of r and theta? So since there's no x squared plus y squared equals r squared here, then perhaps what we're going to do here is, because our equation is y equals x, let's just take our x and replace it with r cosine theta, and y, we'll replace that with r sine theta. Now I am going to warn you that these examples are similar, okay, and the methods that we use here are methods worth paying attention to. So with our y equals x here, let's go ahead and start with this. I'm going to kind of tear this off on the side here. We say y equals x. What we're going to do is we're going to replace our y value and our x value with the r sine of theta and the r cosine of theta respectively here. Now, In other instances here, we might try to set this equal to 0 and factor out this r. But what I'm going to tell you is this. We don't want to lose anything here. So what we're going to do is we're going to divide both sides by r cosine theta. And by doing this, what I want you to see is what we get on the right is just a 1. And on the left side, we notice that our r's immediately cancel out and we're left with sine over cosine, which is a fabulous thing because we have tangent of theta equals 1. Now, when you are writing the equation from something into rectangular to polar, what we're going to say is this. If there's no r in this equation here, then get theta by itself. So we're going to make a note, and we should make this a big time note, so we'll change our ink to red here. Red. If, block this off here, if no r value in the polar form of the equation, polar form of the equation, then solve for theta. So the neat thing about this here is that we can solve for theta. We could say that if we take the tangent inverse of everything on the left, so the tangent inverse of the tangent of theta would be the same thing as the tangent inverse of everything on the right here, 1. We get that then just theta equals the tangent inverse of 1, which comes out to be pi fourths here. The only reference angle we get where tangent is a positive 1 is at 45 degrees or pi fourths. So what I want you to see is that if we were to go graph this here, check this out. You would literally be graphing all of the points in polar form that have an angle of pi fourths. We can see that all points in polar form, no matter what their r values are away from this middle pole, have an angle that is pi fourths in one way, shape, or form. So let's take a look at our other two examples here. What we're going to do is very similar. We're going to switch out our x's and y's, and we're going to talk about some techniques we have for solving these. So we say y equals x minus 2. Let's go ahead and start by replacing y with r sine of theta. And this is going to be equal to r cosine of theta here, minus 2. And so working with something like this here, our method this time is going to be slightly different than the last equation where it was just y equals x. And now the difference here being that this y equals x was just y does equal x. Here we have kind of this constant in the way. And so what our method is going to be, instead of dividing everything through by r cosine theta, like we did in the last one there to obtain our tangent of theta, what we're going to do is we're going to subtract this r cosine of theta just over to the left-hand side. And really our ambition is going to be to get anything that has an r in it by itself. So we have r sine of theta, okay, minus r cosine of theta. And this is all equal to, in this case, just a negative 2. And so the neat thing about this is because we want everything in terms of r and theta here, really what we want to do is isolate r. I guess it is all in terms of r and theta. So let me be clear on this one here. Down here I wrote, if no r value in the polar form of the equation exists, then solve for theta. What we're always doing when we write things in polar form is isolating the r. So we want, let's make sure we make a note here, want to write polar EQs as r equals a function of theta. Some function of theta here, if I can get that to go away. There we go. Or in other words, we could say like something like r equals, 4 sine of theta, We could write something like that as an example here. So we need to isolate r. So what we're going to do is we're going to factor out our GCF here. And what we get left with on the inside is the sine theta minus cosine of theta. And this is still equal to negative 2. But what we're going to do is we're going to go ahead and just divide by this factor here, sine theta minus the cosine of theta. And so by doing this, by dividing by this entire value here, we get it to cancel out on the left side. We're left with r equals negative 2 over the sine of theta minus the cosine of theta. And this right here would indeed be the graph of the line y equals x minus 2. Now, if we had graphed that in rectangular form, let me get my grid back up here. Desmos. And we graph this, we say y equals x minus 2. Let me pop back over to rectangular form. You can see that in rectangular form, its y-intercept is negative 2 and it has a slope of 1. If we were to put this into polar form now, we got some funky equation, didn't we? We got r equals, and I believe it was negative 2 divided by. So now what we're going to type in is we're going to type in, let's see here, functions. We have the sine of theta. Here's our theta, end parenthesis. So I suppose, I'll just do it this way, minus the cosine of theta. Let me go back and put in my theta. I can just type a lot faster there. There's our theta. Check it out, man. Like this, and this, and this, and this, and I turn this one off, and that's that one, and they're really the same equation, okay? So this last example, y equals 4. Again, this is kind of another instance here where there's just kind of a method that we use in order to convert this into polar form, but then you start to pick up on some patterns, okay? So with our y here, again, here's what we want to do. Let's rewrite our y as r times the sine of theta. Congratulations, everything here is in terms of r's and thetas. Now, remember what I mentioned up here, we want to write our polar equations as r as a function of theta. So what we want to do is isolate r, get r by itself. So we're going to take both sides of this equation here, and we'll divide by the sine of theta. And so what we end up with is this equation r equals 4 over the sine of theta. And again, to graph y equals 4, that's an interesting situation. We're graphing in rectangular form the line that contains all the points having a y value of 4, in other words, a horizontal line. When we go graph this in polar form, we have 4 over sine of theta. Let's take a look at these equations here. We have y equals 4, and so you can see our horizontal line with a height of 4. But if we say r equals 4 divided by the sine of our angle, and we're going to call our angle, of course, theta here, you can see that we get the same, precisely the same line there. So these are just some really good examples to know how to convert from rectangular to polar form. And remember that we can always rewrite x in terms of r cosine theta and y as r sine theta. Cheers.